Hello, everyone. Welcome to my talk, Ultra-Fast Java in-memory database apps and microservices. In this session, you will learn how you can build the ultra-fastest database applications and microservices on the planet with pure Java. My name is Markus Kett. I'm CEO and co-founder of MicroStream, the open source project and the company behind the open source project. We also contributed to the project Helidon. And I work with Java since almost 20 years now. We have worked on Java development environments. We built the RapidClips Java development environment that is also available as open source. We worked for around 6 or 7 years now on improving the JBoss Hibernate tools for Eclipse to make database development with Hibernate easier for RapidClips developers. We wanted to build Java applications faster than ever before. So this was our goal. However, we were not that successful with improving the JBoss Hibernate tools because the core problem of database development of today, and this is the reason why we started the MicroStream project, to build something fundamental different that is much faster and much easier to implement than all other storage techniques on the market available for Java. First of all, I like to talk a little bit about these core problems of database development of today and the challenges we have by using today's storage technologies. And then how we can use in-memory computing and how powerful in-memory computing is and system prevalence to build really fast and really incredible fast database applications. Then after that, I will talk a little bit about the concept of MicroStream, the Java native persistence. I show you a demo, and after that, how MicroStream fundamentally works. And then we will, I'm sure, have some time for Q&A. So our goal with MicroStream, with the MicroStream project, was to increase productivity, your productivity as a developer, performance of your applications, and to minimize your costs of development and costs of infrastructure. MicroStream is open source. The code is available on GitHub. You can download it via Maven very easily. And MicroStream is also part of Project Helidon, which is a great framework for building modern cloud native microservices with Java. It comes with 2 flavors, Helidon MP, which implements the microprofile standard, and Helidon SE, which is a reactive microservice framework. So it's both flavors are open source. You can download it also very easily. The code is on GitHub, so check it out. We are working very close together with the Helidon team. We are also working together with the Open Liberty team at IBM, with the RapidClips team, working on the visual Java development environment based on Eclipse. We also work together with Payara and with Azul. The MicroStream development started in 2013, and 2 years later, we used MicroStream in production for the very first time. And so today, MicroStream is already used by many enterprises out there building their database applications. So MicroStream is really stable. Yeah, you can now download it and use it for your enterprise business applications. The MicroStream as a company is the main contributor to the open source project. We provide a large task coverage and an update warranty and support for enterprises. Now let's talk a little bit about the core problems of traditional Java persistence to understand the challenges in database programming of today and how we can improve Java persistence fundamentally. In Java, everything is an object, so everything is object oriented, and we love to use objects. However, as soon as we want to store data, then we are used to use external database systems, and they work totally different, fundamentally different to the Java object model. It's not possible to store complex object graphs in flat tables from the technical perspective. It's not possible. So we're in trouble. We have several impedance mismatches here. For instance, the granularity mismatch. So the object model can be much more granular than the relational model that provides tables and columns only. Then inheritance is not possible in the relational model. We have an identity mismatch here. In the relational model, we have to use a primary key. This is not mandatory in the object model. We have an association mismatch. So the associations are not bidirectional in the relational model. Navigation through an object model is very easy. It's not possible in the relational model. We have to use SQL joins here. And then we have data type differences. Java comes with some primitive data types, but database systems sometimes provide more than 30 specific data types we have to handle. So lots of differences. And what's about the NoSQL database systems? Are they better? I would say they are different. They now introduce new database-specific data structure or formats like key value, column stores, JSON, graphs, and also proprietary object models. But all these database-specific data structure or formats are also incompatible with the object model, with the Java object graphs. So we have the same technical problem and technology break here as well. For the relational model, we solve this problem by using a kind of like bridge. So we use object relational mapping frameworks to enable storing objects in a relational database. For the NoSQL databases, we need a data conversion and convert data in the database specific data formats. And yeah, vice versa, we have also a data conversion or code generation. Yeah, which means we have code generation and data conversion through every single read and write. And this is really a problem because this leads to latencies. It requires lots of computing power. It reduces your performance. Yeah, it forces you to use complex frameworks or implement custom mappings. So this makes your development process more complex, increases the cost of infrastructure, and increases the cost of development. And really in any case, we will have millisecond query times. To increase our performance, we are used to using memory computing, because in-memory computing is really powerful. So in almost all database applications, in-memory computing is used. So what we can do is we can add a cache, and Hibernate introduces a second level cache, and you can use EH cache, for instance. However, this cache is not that fast as you would expect, because it's in-memory computing. It's an in-memory computing feature. However, the objects are serialized into the cache and has to be deserialized when you read the data from the second level cache. And this leads also to a latency and reduces the performance of your application. So, which means Hibernate applications are mostly not that performant, even if you use a cache. In practice, what we do is, we add sometimes another caching layer. So now you can try to improve your performance by adding a distributed cache. You can also add, for instance, an in-memory data grid, or use an in-memory database. You can also use event streaming like Kafka. But all of these distributed systems are also incompatible, or their formats are also incompatible with Java objects. So we have the same problems here as well, which means no matter which storage solution you use, all these storage solutions are incompatible with native Java object graphs. So we are in the cloud, which means if you have performance issues, you won't work on the core problem, right? So we are used to add some more machines, and then we scale horizontally and distribute the load of the application. This is very common, and especially in the cloud. However, the cloud costs will explode, so your infrastructure costs will increase more and more. And on the developer side, we have to deal with two different data models. You have to care for your classes. You have to implement the database specific data model. We need a data type mapping. You have to deal with an object relational mapping framework like Hibernate, adding one or even more caching layers, in-memory data grid, distributed caches, local caches. You have to care for all these cache configurations. And then we are strongly limited in terms of our data model. In Java, you can build very elegant object models. However, you have to adapt your object model to the database specific data model or format, which means you're limited. Then we mix completely different paradigms. So we mix the object-oriented paradigm we love, and with the relational paradigm or NoSQL database paradigms that are different to the object models. In Java, in database systems are always heavy by dependencies, testing is effortful, and also the deployment process. Now let's come to the core problem. As long as the systems are different, we will have a technology, we will have really a hard technology break. And so, which means every developer will sooner or later get to the point where his solution no longer meets the following requirements: maintainability, performance, or intelligibility. With memory computing, we can try to solve this core problem. And why should we use memory computing? Now let's have a look on these beautiful numbers here. It's from Jay Boner on GitHub. Here we can see in-memory computing is really fast. So access to memory takes only a microsecond or some microseconds. In comparison to access to a hard disk, in-memory computing is up to 1,000 or sometimes up to 10,000 times faster than access to a hard disk drive. And this is really incredible. Let's talk about system prevalence. Have you ever heard system prevalence? System prevalence is an architectural pattern, and it combines the system images and transaction channeling to provide speed, performance, scalability, transparent persistence, and transparent live mirroring of computer system state. In a prevalent system, the state of your application or service, which means your objects, are kept in memory in a native format. And all transactions are channeled, and system images are regularly saved to disk. Which means the architecture is very simple and clear. We have our Java application or service, microservice written in Java. We have our objects in memory, which is our system state. And now we can use, for instance, Java serialization to create a snapshot and store the system state persistently into a file storage. The advantage here is we only have to deal with our Java classes, no more database-specific data structure or formats. This is really a simple concept, simple architecture. And now we are able to use the object graph in memory as an in-memory database. And now we can query the object graph in memory by using Java Streams API. And this is very powerful and really incredible fast. However, system prevalence, especially the initial system prevalence approach, is linked to many challenges. And perhaps this is the reason why system prevalence is not that popular in practice. For instance, to create snapshots all the time, this might not be a good solution. The snapshot size mostly will be too big. Your database size will be limited to your RAM size. The snapshot time can take too long. To restore the system state can take too long. And this concept is not suited for microservices, because with microservices we need a very fast startup time, and you will produce lots of traffic by generating snapshots all the time. Then there are lots of unanswered questions like, what is if my classes change? And if I deal with bigger memory sizes, will I run in garbage collector issues? Lots of questions. And this is the reason why system prevalence is not that popular in practice. Now, with MicroStream, we have eliminated all of these problems. And this is the reason why we sometimes call MicroStream System Prevalence 2.0. And now with MicroStream, you're able to build really ultra fast applications that are highly efficient and they save you costs. And MicroStream or applications, database applications with MicroStream are very easy to implement. Let's have a look on how MicroStream works. The architecture is very simple. You have your Java application. It can be a monolithic application or a microservice written in Java. Then you have your objects in memory, and MicroStream is really built for, you can deal with simple objects, simple object graphs, but it's built for high complex object graph with circular references, so everything is possible here. So build any Java object graph in your memory, keep it in your memory, and with MicroStream you're able now to persist any object and even subgraphs, and vice versa, load any object reference or subgraphs into the memory, and MicroStream merges the object reference directly into the object graph, so you don't have to deal with object copies. You can store your objects in a plain file storage, but you also can store your objects in a relational database or in any NoSQL database system. You can use an in-memory data grid as your persistence strategy. You can use a distributed cache like Redis. You can use event streaming like Kafka. Because we store binaries, there is no more mapping or data conversion at all. So we store binaries only. And so data conversion is eliminated. The architecture is super simple. You can query now the object graph in memory with Streams API. And you do not have load the entire database in the memory, because you can use lazy loading and load only some subgraphs into the memory. And creating an object graph with streams is really incredible fast. It takes only microseconds. So we talk about microsecond query time in comparison to milliseconds with SQL or NoSQL database systems. So if you cannot believe that performance, so we have performance demo here. Here we have two applications running in parallel. So one application is built with Hibernate and cache. So we have here a hot cache. We have 250 gigabyte database. It's an Oracle database, and the application is a bookstore demo. So you can find the code on GitHub, you can download it and check it out and play around. The other application is built with MicroStream. Here you can see the query code of each query. And all queries are executed sometimes 10x, sometimes 100x, sometimes more than 1000x faster with MicroStream, and in comparison to Hibernate and cache. And this is really incredible. So this saves you lots of computing power, and so you can handle much more load, or you do not need that many machines. So you will save lots of infrastructure costs with MicroStream. What actually is MicroStream and how does this work? The core of MicroStream is a serialization that is written from scratch. So we built a fundamentally new serialization that is up to 20x faster than the Java serialization. On top of that, we built persistence framework for the JVM, and we have also an implementation for Android. On top of that, we provide a legacy type mapping that handles your class changes automatically behind the scenes. Then we provide a file system garbage collector that cleans up your storage behind the scenes. We added a file system abstraction, so MicroStream can run everywhere, and your file, your storage target can be also anywhere else. Then we provide database connectors. We provide a REST interface that enables you access to your storage data, and a graphical user interface that allows you to browse through your storage data. You get some native backup functions if you use plain file storage. If you use a database system, then you can use the backup functions that is provided by the database system, of course. And you get converter, for instance, CSV, and we're working on JSON, protocol buffers, Afro, and furthermore. And all together, this is MicroStream. We provide connectors to various database systems, and further connectors are work in progress. You can run MicroStream wherever Java runs. The only requirement is Java version 8, and it also runs on GraalVM native images, so you can use it as a persistence, as a micro persistence for your microservices. And as I mentioned, it also runs on Android. You can use it not only with Java, but also with any JVM language. MicroStream is really super simple to and very convenient to use. There is no storage technology out there that is similar, easy to use than MicroStream, because there are no annotations. There is no specific superclass. You do not have to deal with specific interface you have to implement. Just POJOs. So use your classes as they are. This is really super simple. Yeah, you can use inheritance. This is really trouble-free. So yeah, just use POJOs. That's really simple. You can also store any Java type. You can use any types of any third-party API. So no limitations here in terms of your classes and your data model. Build your data model freely. So yeah, you're not forced to adapt your object model to any database-specific models. Yeah, you can really build your object graph freely, use circular references, use inheritance if you like, use collections, use any Java type, and yeah, you can use any Java library. The only thing you need, or the first thing you need, is a MicroStream instance, and it creates a root object. Then your object graph is similar to a tree, and then you can add objects to this root object. And of course, you need a persistence target, plain files, a database system, so you can choose. Then you can add any object to your root object, and you only have to call one method. It's the store method if you want to persist your objects. And each store is an atomic none or nothing operation. It's transaction safe, and it adds your objects in a highly optimized binary format appended to your file storage. So we have a append log strategy. So each store is stored, appended to your file storage. We never overwrite data in a file storage. This is very important to mention. So we add some object here, and we store it, and then we store a new binary file in the file storage. We add some more objects, call the store function, the store method again, and we store another binary file to the file storage appended, and so on. So we add some more objects, we store it, and a new blob is stored, appended to the file storage. So this is really simple. We never overwrite data in a file storage. If you want to change some objects, you can do that anytime. You change the objects in memory, and then you call the store method. And here as well, a new binary is stored, appended to your file storage. So if you create an object, a new object, or if you change an object, the store method will write a binary file appended to your file storage. When you start your application initially, then MicroStream loads all informations of your object graph into the memory. But no data are loaded into the memory. Only the object IDs are loaded into the memory. Then you will get the complete structure of your complete object graph in memory. Now, you can decide which object references you want to load eager, automatically, and which object references you want to load on demand by using lazy loading. So if you use eager loading, then the object references are loaded initially through the application start. You can do that, but you do not, it's not mandatory. So you can also use lazy loading only. So you never have, this is very important, you never have to load the entire database in the memory. So, so this is also very suited for microservices to provide a fast startup time. Lazy loading is also very simple. So if you want to load an object reference, then just call a get method. So you call the get method, and MicroStream cares for the rest and loads the object reference automatically and merge the object directly in your object graph. So you do not have to deal with object copies. This is very convenient. So you don't have to deal with selects, classic selects like in relational databases. So it's fully object oriented and a very convenient programming model. Just call the getter and MicroStream loads the objects into memory. Call the get methods, it loads the object reference, mostly subgraphs, into the memory. And the JVM cares for the memory management. The lazy references can be cleared anytime. So if you want to save memory or clear your memory, then you have fully control of your lazy references and clear your lazy references anytime. And if you call the get method again, then MicroStream loads the object reference from the storage again. Very convenient. I mentioned already the in-memory, the object graph in memory is our in-memory database, and we can query and search object graph with Streams API. You can use parallel streams, and the JVM is so incredible fast that even if you have really complex object graphs, it will mostly take microseconds. So we talk about microsecond query time up to 1,000 times faster than the comparable JPA query. What is if my classes change? And we do that all the time, right? So if we change our classes, then MicroStream loads an object, the MicroStream recognizes automatically that the class has changed, and MicroStream will handle these changes automatically in terms of primitive types. It can be handled automatically. If you have more complex objects, then you can add a legacy type mapping, a custom mapping, and this is solved through runtime. And then you have to call the store method again, and then the new version of your object will be stored, appended to your file storage. So if MicroStream recognizes that the class has changed, then the already stored object, the older version, becomes a legacy type, and you store the new version of the object by calling a store method, and MicroStream will append the new version of your object to the file storage, and then we will have versioning automatically. So you get a versioning automatically of your classes. And now as I mentioned, we will change our classes all the time, so we're used to use it, of course, and which means your storage grows more and more. But with our garbage collector, this is not really a problem. Sometimes you will have lots of legacy types in your file storage. So if you don't like, or you don't need versioning of your classes, then you can remove or let the garbage collector remove the legacy object from your file storage, and then the garbage collector keeps your storage clean and small. You can configure the garbage collector, and it works automatically behind the scenes in a separate thread. Removing objects is very simple. So you just remove the object reference, then the object will be removed by the garbage collector of the JVM, call the store method again, and then you will have stored the new object. It's important to mention that you have to store always the owner object. So if you change objects in a collection, for instance, then store the collection. MicroStream provides channels, so you can parallel your I/O operations, and so you're able to accelerate all of your I/O operations, by using channels. If you do miss anything in MicroStream, then have a look on the great Java ecosystem. You can use any Java library and combine it with MicroStream, for instance, GraphQL for writing queries, and enable external applications to access and query your object graph. You can use Lucene to implement a full text search, and if you want to build up and deal with huge memory sizes, and you have concerns about garbage collector pauses, then you can check out Azul JVM. Up to 20 terabyte of memory can be handled by the Azul JVM, and that's really incredible. Rules and challenges. With MicroStream, we have to think a little bit different. So because it's a paradigm change, in a paradigm shift in database development, because now your object graph in memory becomes your in-memory database. In the traditional database server paradigm, your database is located on a remote server, and the queries are executed on a remote database server. And your persistent data are also stored on a remote database server. With MicroStream, this is different, because now your database, the object graph in memory, is your in-memory database. It runs within your application's JVM process, and the queries are executed in your application. And so all queries are executed in your JVM process, and only the binary data are stored in a file storage or in a blob storage or even if you use a relational database, then you will use the relational database only as a blob storage. No queries are executed anymore on a storage. This is very important. Do I have to load my entire database in the memory? No, that's not mandatory. You can do that if you have enough memory size, or your database is small enough, and you do not develop a microservice. Of course, then you can load the entire database in the memory. If the startup time is not that important, so if you build a monolithic application, you start it once and run for 2 years or so, then you can do that. If you want to build microservices, you need a really fast startup time. You start the services in milliseconds, then you should not load too much data initially in the memory. And in most cases, we know the database is bigger than the memory size. And let's say you have 1 terabyte of database size and only 4 gigabyte memory, then use lazy loading. Or if you want to develop a microservice, then use lazy loading only to load your the data on demand into the memory. Then next rule, we also have an architecture rule. If so, MicroStream is a single storage instance or a single node storage, which means one application node can store data into one storage, and also one application node or one microservice node can store data in multiple storages. So you can for sharding, for instance. So it's always possible and easy to shard your object graph. And it's recommended to do that. However, you must not start multiple instances of your application or service and let these instances store data persistently into one and the same storage. So here you will run in concurrence issues. You must not do that. We are working on a cluster, on object graph replication that enables you to build distributed apps and microservices with MicroStream, but this cluster is still in progress. Memory management, I mentioned this already. Let the JVM care for memory management, so you do not have to care for that. You have full control of your lazy references. You can clear them anytime. In terms of garbage collector issues, check out OpenJ9 JVM or the Azul JVM. So memory management is not a problem. Challenges with MicroStream, yes, there are challenges because MicroStream was built for Java developers and was built for fitting seamlessly with the object model to enable fully object-oriented programming, database programming. It's not suited for DBAs. So it's a paradigm shift in database programming. Think like a Java developer. Please forget everything you have ever heard of relational databases. It does not support SQL queries. We can use core Java, and MicroStream is built for using core Java features instead of database-specific features that compete with core Java features. MicroStream is a storage engine that stores your object graph. And that's the job of MicroStream, built for separation of concerns. It's not the database management system. So your application becomes the database management system and has to cover database management system tasks. For instance, you have to care for validation and you have to care for concurrency. This is important to mention here at this point. Beyond persistence, MicroStream can be used as a pure serialization that is super fast and highly secure, by the way. Conclusion, MicroStream was really built for high productivity, high performance, and minimizing your costs of development and costs of infrastructure. It's open source. We work on a MicroStream cluster. We work on a MicroStream cloud, providing MicroStream as a service and MicroStream cluster as a service. We work currently on MicroStream serialization for serverless functions and further database connectors. So if you want to learn more about MicroStream, and you can find MicroStream on our website, microstream.one. The code is on GitHub. Check it out, play around a little bit with MicroStream and build the fastest and incredible fast database applications with pure Java and also microservices with pure Java. Thank you for joining and have a great day on the conference. Thanks for having me.